inaugural section, but I would like just to emphasize that Navas, indeed, his works focus on iterations between theory and dynamical systems, with incursions in geometry. His major component is related to group actions on manifolds, in particular one-dimensional manifolds, the circle and the real life, proving many beautiful and vivid results. And he wrote a beautiful book on this topic that covers from the really beginning of this theory to the most recent results, providing a great overview of the research on differential group action on the subcircle. For sure, Navas would be working at the most prestigious places, but he decided to stay at his home university, the University of Santiago, Chile, where he is permanently involved in promoting mathematics, organizing school, as well conference, and his influence, however, contributes enormously to a step forward of mathematics in Chile.
Okay. Okay, so thank you very much for this very nice presentation. I will speak about groups and, well, I am not assuming that you are a specialist in group theory, not even interested in groups. So I will start by trying to convince you that groups are actually important for mathematics. For this, I will just quote Poincaré, the great Poincaré, who claimed that groups are not only important in mathematics. Actually, groups are a central object of mathematics. At the point that the core of mathematics is, just something concerning groups. This is for the translation of this very nice French sentence. So, Poincaré claimed this when he was discovering, inventing what he called function and training groups. And it is quite remarkable that at the very same time, he was inventing another major and deep area of mathematics, namely dynamical systems. And by a nice ways of coincidence, this talk is aimed to be, I will intend to establish a little marriage between groups and dynamics. Okay, so, but it's a little bit difficult to do so if we start with the classical definition of groups, namely a set with an operation and so on. But what I would like to emphasize here is that this is an axiomatic definition of what was in the minds of mathematicians in the 19th century. And actually, the realm of groups is that every group is a group of transformations. And with this axiomatization, this turns to be a theorem, the Cayley, which is almost trivial to prove. Okay? So everybody knows the proof of this theorem. Every group is the group of transformation of something, namely the group acts on itself by left translations, and this is a faithful representation. Okay? Actually, one can somehow visualize this action by looking at what is called the Cayley graph of the group, which is the graph where the vertices are the element of the group, and you connect any two elements if they differ by right multiplication by a generator. So the Cayley graph depends not only on the group, it also depends on the system of generators, but most of the important properties do not depend on the system of generators, provided, for instance, it is finite. So for instance, this is the Cayley graph of the C to the square with respect to the canonical system of generators, and well, here the Cayley action is realized just by translations in the plane. And this is the Cayley graph of the free group with respect, again, to the canonical system of generators. This is just a tree because there is no non-trivial relation. it's a little bit difficult to visualize the Cayley action here because this is not the right geometry for this Cayley graph. So the right geometry is the hyperbolic geometry. And if you visualize the Cayley graph in this way, you can realize the Cayley action as an action by isometries of the hyperbolic disk. Okay, now if you look carefully at these graphs here, you will notice that they have many symmetries. So they have symmetries that do not come from translations in the group. So for instance, you can flip the generators. This is not a translation group. So this issue was addressed by this guy here, so Roberto Fuchs. So to be honest, I just learned about the life of Roberto Fuchs by looking at one of the spots of this conference. So I didn't know that actually he spent most of his life in Chile. And actually, he was one of the founders of the Chilean Mathematical Society. So he left Germany at the end of the 30s by obvious reasons. Then he went to Italy, then he passed to Argentina, and finally he went to Chile, to Valparaiso, and he proved a very nice theorem that I would like to show here. So given a group, say a finite generated group, there is a graph such that the full group of symmetries is exactly the group that you had at the very beginning. Okay, so you can somehow kill the extra symmetries that come in the Cayley graph. Actually, there is not only one graph, there are uncountably many graphs for any given groups. So for instance, in particular, this applies to the trivial group. So there are non-trivial graphs having trivial groups of symmetries. Okay? And there are uncountably many, but this is one of these. This is a famous graph. This is the Fuchs graph, which is, in a very precise sense, this is the smallest non-trivial graph having trivial group of symmetries. Okay, so we know that every group acts on a certain space. Actually, every group is the group of full symmetries of a certain space. And here there is a general principle that applies. Namely, you take a group or a family of groups with some properties, you make this group act on a certain space in a nice way. If you are able to do so, then you will certainly get a nice theorem. Okay? This is a general principle in this stuff. And of course, we need a definition of what is nice here. So an example of nice space is, of course, the Cantor set. This is very nice, for example, in symbolic dynamics. And at this point, it's worth to point out that every group, say every countable group, is a group of homeomorphism of the Cantor set. So for instance, take gamma, assume that gamma is infinite. So take this space here, the space of sequences of zeros and ones indexed by gamma. This is a Cantor set with the product topology, and the group acts on this space just by shifting the coordinates. This is an action by homeomorphisms. So in some sense, the group of homeomorphism of the Cantor set contains the whole of group theory. Okay, so this is not just a remark, this is a very important action, but I will not discuss this. So let me say that for finite groups, well, there are many ways to change a little bit this action, because this is no longer a Cantor set. You can, for instance, you can add some extra coordinates in an artificial way, but I prefer this solution. So let us consider the dyadic metric on the Cantor set, okay? And let us consider the group of homeomorphism of the Cantor set such that there is a decomposition, for every element, there is a decomposition of the Cantor set into dyadic Kloppen sets, and the restriction of the element to this Kloppen set is just an affine transformation, a dyadic affine transformation. So this picture here is aimed to represent the following. So the boundary at infinite of this tree here is the Cantor set, and this, or the tree starting from here, correspond to a Kloppen set in the boundary, and the Cantor set, and the element here is moving the Kloppen set corresponding to this part of the tree here into this one into this one, this one into this one, and so on. So this is a homeomorphism of the Cantor set. And this gives you a group of homeomorphism of the Cantor set, which is actually quite remarkable. This group was introduced in the 60s by Richard Thompson, and here are some remarkable properties of this group. Well, this group, first of all, this group contains a copy of every finite group. this is more or less obvious because you can permute in an arbitrary way these Kloppen sets. So it contains a copy of every finite group, so this solves this little problem here. But what is more important is that this group is finitely presented, which is quite remarkable. So it has a finite system of generator, and not only that, there are finitely many relations such that every non-trivial relation in the group can be deduced from these relations. And this group is simple. It has no non-trivial normal subgroup. Actually, this was the first example of a group having these properties. An infinite group which is finitely presented and simple. This solves a non-standing equation in group theory. And well, it has many, many other properties, and let me just add one of these. So every automorphism of this group is inner, so every group automorphism is obtained by conjugacy inside the group. By the way, this group contains two remarkable subgroups. Well, this group is denoted by V. This is the standard notation, and it contains two remarkable subgroups. For instance, look at this picture. So this picture is very special. It represents a very special element in the group because it sends the first Kloppen set into the first one, the second one into the second one, and so on. So you are not permuting in an arbitrary way. So this element belongs to a special subgroup of Thomson's group, which is Thomson's group F. So the two subgroups of Thomson's group are the following. The elements of V that respect the cyclic order of the Kloppen set, they form a subgroup. This is denoted by T. And what is special with this group is that this can be seen as a group homeomorphism of the circle. Because instead of starting decomposing the Cantor set into dyadic subsets, you can imagine that you perform the same construction in the circle and you decompose the circle into dyadic intervals, and you play the same game. And there is another subgroup, so the subgroup of elements that preserve the linear order of the Kloppen sets. And again, this is a subgroup, and this is naturally a group of piecewise affine homeomorphisms of the interval. Okay, because again, you are preserving the linear order on the interval. And these two groups are really remarkable. So for instance, these two groups are finitely represented. This is an explicit presentation for this group, Thomson's group F. These are the generators. These elements here, F and G. And these are the relations that determine every relation in the group. Okay? So please keep in mind these groups because they will appear a lot during this conference. These are really remarkable objects. Okay, so let's now try to do something more general, or not exactly the same, but something quite related, but giving some freedom for the maps you are using. So let us start with an arbitrary homeomorphism of the Cantor set. And let us consider the following thing, which is called the full topological groups. So let us consider the group of homeomorphisms of the Cantor set, such that for every element there is a decomposition of the Cantor set into Kloppen subsets, such that the restriction of the element to each of these Kloppen subsets is a power of the original homeomorphism. So in some places it is equal to F, in some places F to the square, F to the -3, the identity, and so on. Again, this is a group. And of course, this group will have an algebraic structure that is going to depend a lot on the original homeomorphism F. Okay? So here is an example of theorem that appears in this context. So this is a remarkable and quite recent thing by many people. Some people did some of the stuff, some other, the other. So if you start with minimal homeomorphism of the Cantor set, there are many ways to construct this kind of thing. You start with any minimal homeomorphism of the Cantor set and you perform this construction, then you get the full topological group. This group turns to be, or at least the commutator subgroup, turns to be finitely generated, simple, and amenable. And again, this is the way how a long-standing question in group theory was solved. Okay? So let me remind you what is amenability. This is one of the most important notions in group theory. There are many, many equivalent definitions. This is one of the possible definitions, which is, I think, it's well adapted to this talk because it's the dynamical definition. So a group is amenable if and only if you have an action of this group by homeomorphism of a compact space, then there is an invariant probability measure. Okay? So for instance, the group of the integers is amenable. This is a classical theorem by Bogolyub and Krylov. And nilpotent groups are amenable, solvable groups are amenable, and the reason is that when you start with an amenable group and you start taking unions or extensions, then you stay in the amenable board. So extension of an amenable group by an amenable group is amenable. So this is the way in which one can see that solvable groups are amenable. So what is the key part of this theorem is that, well, if you do that, if you take extension of amenable groups, then certainly you will lose simplicity. If you start doing unions of an amenable group, then quite probably you will lose this property of being finitely generated. So the existence of such a group is quite remarkable, and it says that somehow we still do not understand amenability at all. Okay? By the way, let me just mention that it is not exactly trivial to see, but it is not too hard to see that amenable groups cannot contain free subgroups. Okay, so the free group is not amenable. This is obvious because you can construct many actions without invariant measures. So, and an amenable group cannot contain free subgroups. In particular, in these full topological groups, there are no free subgroups. So if you take two elements, then there is any two elements. There is a non-trivial relation among them. And what is quite remarkable again is that so far there is no explicit way, there is no procedure to detect non-trivial relations in the group. Although we know that they exist because the group is amenable. Okay. This is a quite remarkable fact that is provided by the proof of this theorem, which uses very deep notions in functional analysis. By the way, this reminds me another question that I think is due to John Frank's, whether the group of intervals exchange transformations contains a free subgroup or not. Okay, so let me now leave the Cantor set. I will pass to higher dimensions. And by this, I just mean that we would like to develop a general theory of groups acting on n-dimensional manifolds. However, for the rest of my talk, I will restrict to the one-dimensional case. And the reason is the following. In higher dimension, almost nothing is known in full generality. Of course, if we impose some extra conditions, for instance, there is an action with a geometric structure which is invariant, some measure which is preserved, and so on, there are many deep and general results. But if we just want to deal with the structure, with the algebraic structure of group of homeomorphism of diffeomorphism of manifolds, there is no general result in higher dimensions. So let me illustrate this fact by a single question that I like very much, which concerns torsion groups. So Burnside, in the 30s, I think, he asked the following question. Take a finitely generated group. Suppose that every element has finite order. So every element is torsion. Is it true that the group is finite? And he dealt with this question, and he proved that the answer is yes for linear groups, for groups of matrices. And he left open the general question. Actually, there is a strong version of this question where you impose not only that every element has finite order, but the order is uniformly bounded. Okay, say every element has order 7, 8, or less than that. And to deal with this strong form of this question, it is quite natural to introduce this group, the Burnside group Bn, which is a group, say, generated by two elements, A and B, and you impose the relation that every word in the group to the power n is equal to the identity. Okay? So this is, of course, a torsion group, because you are imposing the condition of torsion. So you lose, maybe you lose finite representation, but okay, let's concentrate on this group. And the question is whether this group is finite or not. And many answers are known. So V2, V3, V4, and V6 are known to be finite. Okay, so these are nice exercises. Well, this is not an exercise. By the way, this is the Cayley graph of V3. It's a very nice group of 27 elements. For V7, it is unknown whether it's infinite or not, but according to Gromot, it is obviously infinite. Actually, it should be hyperbolic in some sense. However, there is no proof of this fact. For V5, again, it is unknown, but according to Selmanov, it should be infinite. However, it should have a very different geometry from V7. What is known, and what is very nice, is that for very big n, say for n odd and larger than this strange number here, Bn is infinite. Okay? This is a quite remarkable theorem in the 70s by Adyan and Novikov. Actually, it is more than infinite. It's non-amenable, which is much better. Okay, so this is a really fascinating subject, but what I want to keep in mind here is that finitely generated infinite torsion groups do exist. And the question that I learned from Benson Farb, although I think it's a folklore question in this stuff, is whether such a group can be realized as a group of acting on a manifold. Say, very concretely, assume that gamma is a group of homeomorphisms of the sphere in which every element is torsion and the group is finitely generated. Is it true that the group is finite? Okay? Nobody knows. This illustrates the fact that we know very little in dimension 2. Okay? So let me just say two things. If you replace the sphere by the circle, this is an exercise. Not so easy, but this is an exercise. And the question is very nice in dimension 2 from the dynamical point of view, because it is another theorem going back to Kerek-Harto, which is based on the work of Brouwer, Brouwer's translation theorem. If you take a finite order of the homeomorphism of the sphere, it is conjugate to a rotation. So it is a rotation up to change of coordinates. Okay? So the question Farb here asks whether you can somehow put different coordinates in the sphere in a very tricky way so that the group generated by the corresponding rotation is a finite group. It's an infinite group, but every element is torsion. Okay? Good. So now let me go into dimension 1, which is the main subject of my talk. And from my point of view, what is special in dimension 1, one of the features which are special in dimension 1 is that there is a very precise algebraic descriptions of groups and actually sometimes of actions on one-dimensional spaces. And here by one-dimensional space, I mean a one-dimensional manifold, namely the circle, the interval, the real line, and so on. And these are the characterizations. So a group or an action of a group on the real line comes from something which is called a left order. A group acts on the real line by orientation-preserving homeomorphisms if and only if the group is left orderable, which means that there is a total order relation on the group which is invariant under left multiplication. Okay? This appears to be a triviality. However, if you think a little bit, the fact that the free group in two generators is left orderable is not completely obvious. Okay? If you start trying to construct an explicit order on the free group, this is very difficult. However, it is left orderable because if you take two generic homeomorphisms of the real line, they are going to generate a free group. And for the case of the circle, well, this is a little bit more complicated, so let's consider actions without a finite orbit, otherwise we are somehow in this case. And this action is completely characterized in an algebraic way. So the mathematical object is a bounded cohomology class with C coefficients having a representative taking the values 0s and 1s. So I will not discuss this. I will not define the words here. I will just say that this is a theorem due to Gis that I quote here as being the Poincaré-Gis theorem. And the reason is that if you read here the theorem for the case of actions of C, that is actions generated by a single homeomorphism, what you recover here is the Poincaré rotation number of the homeomorphism. Okay, this is why I call this the Poincaré-Gis theorem. Okay, again, dimension 2. Does there exist an algebraic characterization of groups that do act by homeomorphism of a certain two manifold? I think there is not such a thing. Okay, so there is no complete algebraic characterization of this. So, have no proof of this, just the intuition, and it is not even easy to state this question in a very concrete way. But anyway, I think this is really the difference between dimension 1 and higher dimension. And well, now let me concentrate on this, on the left orderability of groups, which is something very nice. And because this allows me to speak about something remarkable that was discovered by Patrick de Hornoy, namely the fact that braids are orderable. Okay, so let me just very quickly remind that the braid group is a group generated by these pictures here. So, okay, so such a picture up to high isotopy defines a braid, and the composition of braids is just putting two pictures together. Okay, and there are some canonical system of generators which are usually denoted by sigma I. The sigma I corresponds to the braid in which the ith and the ith plus 1 strand cross, say to the left here, and they satisfy these relations here, which are these are the proof of these relations. This is the braid relation sigma I plus 1, sigma I equals sigma I plus 1, sigma I plus 1. This picture is the proof. Other generators do commute, and this is actually a presentation of the group. This was the work of the theorem of Artin. So theorem in the 90s by Patrick de Hornoy. The braid group is left orderable. Okay. So when Patrick proved this, he surprised somehow the community. So the ideas of de Hornoy are very special. They come from mathematical logics, actually. And he really surprised everybody except for maybe for one guy, this guy here, Thurston. And Thurston realizes that, well, this is a property of the braid group, so it should be able to prove it geometrically. And actually he came out with a very nice proof of the orderability of braid groups using Nielsen theorem. And the methods are completely different, and this is really a fascinating topic. Just for completeness, let me give the order on the braid group, just the definition. Okay? So in order to find an order on the group, you just need to find what elements are larger than the identity. Okay? And then you need to prove that your definition is coherent. Okay? So larger than identity is what I mean here by positive. And then you have to prove that the set of positive elements that you have is a semi-group, which is disjoint from the semi-group of the inverses, and they fool the whole group except for the identity. So what is the set of positive elements for the de Hornoy order? These are the elements that may be written in the following way. There is some special way of writing the element in the sigma i's, such that the smallest index I that appears is such that the corresponding sigma I is raised only to positive exponents. So for instance, this element is positive because the smallest index here is 2, and the sigma 2 appears only to positive exponent, 1 here and 2 here. You forget other exponents, so here you have sigma 4 to the power 7, sigma 3 is to a negative power, but you don't worry about that. Okay, so this is the definition of the de Hornoy order, but of course there are many things that are behind this definition. For instance, what about this element? Is it positive or negative? Okay. Well, this element is obviously positive because of this relation, which is obtained from the braid relation. Okay. So part of the content of the de Hornoy theorem is that given an expression in the sigma I, you can transform this expression into an expression which is either positive or negative. Okay. And this is the good expression here for the order. And actually, there are algorithms to do this transformation. So this is a question that in which I worked some years ago, which is it was a very nice question by Dale Rolfsen, namely whether the de Hornoy order on the braid group is finally determined. And by this I mean whether there are finally many relations, there is a subset of finally many inequalities in the break group, such that if you take an order which coincides with the Dehornois order in this finitely many set, so it satisfies these finitely many inequalities, whether it has to be the same or not. Okay, and this is quite pertinent, this question, because actually break group have many other orders, and some of these orders, not the Dehornois order, but some of these orders turn to be finally determined. This was the discovery in the 19th by Dubrovin and Dubrovin. What they discovered is that the break group has a very nice decomposition. So there are elements that I call A1 up to n-1, which are not the canonical generators. And the break group decompose in this way. So this is the semi-group generated by this element, the semi-group generated by the inverses, and the identity. Okay? In pictures, the theorem is this, at least for the case of B3. For the case of B3, there is a very beautiful decomposition of the break group. Here, this is the identity element. The green element corresponds to the elements in this semi-group here, which has two generators. The blue elements correspond to the negative elements. With respect to some special system of generators, which again, it is not the canonical system of generators. Okay, and when I look at this question, I remember that I noticed that there was another question in the literature in the same spirit, whether the free group on two generators support a finally determined bi-order. So the free group is known to be not only left-orderable, it is bi-orderable. This is a consequence of a classical theorem of Magnus, and it is not known whether the free group has a finally determined bi-order. And let me give some related results for this question. For instance, if you take the Thompson group F, then the Thompson group F supports some canonical bi-order which is finally determined. There is a bi-order in the Thompson group which is determined by 5 inequalities. And for the case of left orders on the free group, it's a theorem by Maclaurin in the 70s that no left order is finally determined. This was recently extended with a very nice proof by Rivas for free products. Well, this is the case of large groups, say. And for small groups, I proved that this is also the case for nilpotent groups, except for, so this is for, just to avoid in something, except for a trivial case, which is the case of the integers. The case of the integers, well, the integers, you only have two choices. This is the only case that you have to avoid. And the same is true for solvable groups, and this is a very nice recent theorem by Rivas and Teixeira. And the question here is, of course, what about amenable groups? And well, besides break groups, there are many other groups that actually support finally determined by orders, left orders, sorry, and which is really surprising. So I gave a construction of infinite family that later was extended by Ito, and then the Dehornois came with his methods from mathematical logic. So we have a lot of groups here that I like to call the dinos because of the authors, and because they are something like little monsters. For instance, let me give an example. This group has a finally determined left order, and the integer here is any positive integer. Okay, by the way, this group was discovered by Patrick Dehornois. And just to close this, I will not discuss the proof of this theorem. Well, the answer to the Rodson theorem is that it's negative. Actually, the Dehornois order is not finally determined. This is something that I proved some years ago, and later we realized with Bert Wies that a modification of the proof actually applies not only to the Dehornois order, but also to the orders introduced by Thurston using Nielsen's theory. Good. So, well, this is nice, this gives you pictures, but let me put this in dynamical terms. Why left orders, isolated left orders are important, and this is related to a question that I like very much, namely structural stability. So, Remember, an order determines an action on the real line. So if you have a nice order, then you should have a nice action on the real line. Well, let us start with the isolated order of Dubrovin and Dubrovin. And the action that you obtain is very special. It's such that if you take these two generators and if these two generators move the origin into positive real numbers, then you have completely determined the action. Okay? Just translate the stuff about orderability into dynamical terms and you get this. Okay, so this is an action that is determined by very little data. And this is somehow related to a very nice theorem that Gis proved without publishing, because he proved it and he didn't notice that he proved. So there was a proof by Gis and Sergescu in the C2 category, but actually Gis realized that he proved it in the topological category. Namely, if you take Thomson group T, the one that acts on the circle, then it is globally structurally stable. It has only one action on the circle. Okay? So it's a group which is naturally a dynamical group. And again, just to conclude, again, dimension 2. A question: does there exist a finally generated structurally stable group of homeomorphisms, say, of the sphere? I have no idea. Good. So now, well, we have discussed this stuff about orderability and actions on, say, on the real line, on the circle, just by homeomorphism, but let's put some regularity on the action. Let us look at the smooth structure. And, well, this comes from the work of many people, which is inspired by the work on codimension 1 foliations. And actually, it was Thurston who noticed that there is a very big difference between. He found an algebraic abstraction for embeddings into group of diffeomorphism of, say, of the intervals. So there is a general result in any dimension, but for the interval, the statement is the following. If you take a finely generated subgroup of the group of diffeomorphism of the interval, then this group is what is called locally indicable, which means that every non-trivial finitely generated subgroup, well, has a non-trivial homomorphism into R. Okay? And this is especially for the case of C1 actions. So let me just discuss a little bit the proof of this theorem, because this is really a wonderful proof. So the proof is this one. You take an element and you just take the derivative at the origin and you take the logarithm, and this gives you a homomorphism into R. Okay? This is the proof, except for one thing. It may happen that this homomorphism is trivial. And now Thurston came with this wonderful argument. So forget about derivatives. So what you have to do is to renormalize the geometry close to the origin, and doing so carefully, you will always be able to create a non-trivial derivative, provided the group is finitely generated. Okay? This is the proof of Thurston. The rest is just computations. So let me just say that Thurston himself realized that the regularity assumption is crucial for this theorem, so this theorem is not true for group homeomorphisms, and there is a very nice counterexample, or example, whatever you like. So there is a group of homeomorphisms of the real line which is finitely generated and having no homomorphism into R, and this group is the lift to the covering of SL2R of the 2, 3, 7 triangle subgroup. So what is this? So you start with this very nice tiling of the hyperbolous disk. So there is a group that preserves this tiling. This is the 2, 3, 7 triangle group. This is a group of SL2R, which acts on this boundary circle here. Now you open the circle, you get the real line. You just take the cover, and then there will be another group, which is going to be a cover of this group, which acts on the real line, and this group turns to be a group without non-trivial homomorphism into R. This is Thurston's example. And, well, this gives you a non-trivial abstraction for embeddings into the group of C1 diffeomorphisms. Let me just mention that this is not the only abstraction. Actually, there are groups that are locally indicable but do not embed into the group of C1 diffeomorphism of the interval. Okay? So the complete answer, or the converse in a certain sense to Thurston's theorem does not hold. and I'm afraid that there is no complete algebraic characterization of groups that do embed into the group of diffeomorphisms. Okay, now let's consider the class C1 plus alpha. So it is well known that C1 and C1 plus alpha are very different. This is also, this comes from, especially from dynamical systems. Let me just notice that the group of C1 plus alpha diffeomorphisms of any manifold actually is a group, and by C1 plus alpha I mean that the derivative satisfies this Holder relation, this Holder inequality. And again, in the context of groups, there is a very big difference between C1 and C1 plus alpha, which concerns growth of groups. So this is the statement of the theorem. If you take a finitely generated subgroup of the group of C1 plus alpha diffeomorphism of the interval, then it satisfies what is called the Milnor alternative. Either the growth is polynomial or exponential. And this is false for the group of C1 diffeomorphism of the interval. This also holds for the circle and the real line, but this is the difficult case. Let me remind that what is growth here? So growth corresponds to the growth of the balls in the Cayley graph. So you just take an integer n, you count the number of elements that may be written as product of these generators, not using more than n generators, and this is a function of n, and then you say that it's exponential if this growth is the function grows essentially, or you say it's polynomial, it is in between, then you say that the growth is intermediate. And actually there is a wonderful classification of groups of polynomial growth, namely group of polynomial growth are those that contain that contain a finite index subgroup of which is nilpotent. This is almost nilpotent groups. This is a quite deep theorem by Gromov, I mean. So this is, one part is due to Bass and Guivarch, and the difficult part is revolutionary work of Gromov in the 80s. Okay, so this theorem says that either the growth is exponential or you are almost nilpotent. So I will not discuss the proof of this rigidity here in class C1 plus alpha. I will just illustrate what is the example here in class C1, and the reason is that this allows me to introduce another remarkable group, which is due to Grigorchuk. So the Grigorchuk group was the first example of a group with intermediate growth, which was an open question of Milnor, whether there exists a group whose growth is larger than polynomial but smaller than exponential. And this is the example. So again, this is a group of homeomorphism of the Cantor set, actually of isometries of the binary Cantor set. You look at the Cantor set that is set of, as the boundary of the dyadic tree, or which is seen as the infinite sequences of zeros and ones, and these are the generators of the Grigorchuk group. This corresponds to 4 elements, A bar, B bar, C bar, and D bar, and the action is the following. A bar corresponds to a flip of these 3. So it's an order 2 element. And B bar, C bar, and D bar, they fix these 2 levels here. So this B bar is going to fix this vertex here and this one, and the same for C bar and D bar. And once you look at, starting from here, you look at the remaining of the picture, what you see is another 3, and the action of B bar corresponds to the action of A bar. So this means that the action of B bar here corresponds to a permutation here. And the action of B bar on the right here corresponds to the action of C bar that you have to define in this next picture. And again, the action of C bar on the left side is A bar, so a flip. On the right side is the action of D bar that you have to define. So you go to D bar. The action on the left is the identity, and the action on the right is B bar. And there is no contradiction in this definition because you are changing the level. So this is a well-defined group of isometries of the Cantor set. So this is just the definition. I will not discuss the proof of why this group has intermediate growth, but let me just mention that this choice here is a careful choice in order to obtain this property. Okay, so you can put some formulas here. So you can see the Cantor set at the set of sequences of zeros and ones, and the action of A bar, B bar, C bar, and D bar is given by this formula here. A bar just flips the first coordinate, and B bar, C bar, and D bar do nothing on the first coordinate, and B bar on the second coordinate on the left acts as A bar, on the right acts as C bar, and so on. Okay. So this is another way to see the action of the Groucho group. But the group that I want to consider here is a modification of this group, which is quite natural. You will just replace the entries by integer numbers, not only integers mod 2, but integer numbers, and now the action of A is going to be a translation in the first coordinate. And you repeat the very same definition. This is again a group of intermediate growth. This was proved by Grigorchuk, and now what is nice with this group is that this group is naturally a group of homeomorphism of the interval. Why is that? Because you can imagine that in this procedure of cutting the Cantor set into pieces, you replace the Cantor set by the interval. So the fact here that you are considering integer entries means that you are cutting the interval into infinitely many pieces. And then this corresponds to the first level of the tree. Then you go to the second level, in which you are cutting every interval of the first level into infinitely many pieces again, and so on. And then you define the action in a coherent way. So this is a quite natural construction. So this says that this group is a group of homeomorphisms of the interval, and it turns out that this action is C1 smooth. So this is like in the talk this morning by Amy Wilkinson. We know that C1 is somehow very flexible, and one can realize this regularity for this group. But the proof is quite technical because of the other part of the theorem, is that there is no embedding of this group, and actually of no group of intermediate growth, in the group of C1 plus alpha diffeomorphisms. And as I said before, I don't want to discuss the proof of this. I just want to mention that I like very much this statement because, you know, in dynamics, it is known that there is a very big difference between C1 and C1 plus alpha, at least in the context of hyperbolic dynamics. And here, well, we are not in a hyperbolic setting because we are considering diffeomorphisms of the interval, which are very simple. I say the topological dynamics. So every single element is very simple, but if you put them together in a group, then this hypothesis here about growth is like an hypothesis of hyperbolicity. So this is somehow a theorem in the same spirit. So it is not quite surprising that this regularity here should appear. Okay? By the way, the proof is done by using some technique from classical one-dimensional dynamics, namely going to Danjois, but well, we need trivial extensions actually because Danjois theory is in class C2. This is something that we did with my co-authors here, the Ran and Klepsin. And one can do many things. So there are many results in this spirit of classification. So there are classification of nilpotent group actions, and there are also classification of solvable group actions. So well, there are some different regularities here. For instance, this work of Burnside and Wilkinson is in the real analytic setting. My work was in the C2 setting. This recent work is in the C1 setting, and so on. But I don't want to say much about this thing because what is nice here, what is really important is an open question, not the result. And the open question relies on the following. So if you want to classify everything, then you should classify actions of amenable groups. So amenable groups of diffeomorphisms. And it turns out that this question has been open for at least 40 years, whether the Thompson group F is amenable or not. Okay? And well, F, as I define, is a group of a fine homeomorphism of the interval, but actually it fits in this framework because of a theorem of Gis and Sergescu. Well, there is an alternate construction by Thurston that says that this group is actually a group of C-infinite diffeomorphism of the interval. Okay, so it fits in the framework, and you would like to have an answer for this question. And well, there is no answer, except for one thing. If you go to archive, you will find many papers with proofs, and these proofs of amenability of Thomson's group F. Actually, some of them are published with mass review and so on, but it is the general opinion in the community that all these proofs are incorrect, and the question is open. And actually, there are very serious guys with very serious reasons, arguments to think that maybe this problem cannot be decided from a certain logical point of view. Okay, I think that this will be the most beautiful answer to this question. But good, so we cannot classify amenable groups, but we would like to classify everything, so we should do something. What is done here is try to classify groups in the other direction. So we start with small groups. So abelian, nilpotent, solvable, amenable groups, and now we will consider large groups. And here large, well, this depends on the community. A prototype of a large group is this group here, SL3Z. And actually, well, a large group is a lattice in a higher rank simple D group. This is the prototype of what is called a large group. And there is a very beautiful theorem by Dave Morris Witte, saying that this group, and actually any finite index subgroup of this group, cannot act on the circle or in the interval in a non-trivial way. Okay? There is a very nice elementary argument to show this. So there is really a rigidity, there is an abstraction to this group is too complicated to make it act on the circle. Okay? It acts on the sphere because this is, you can make it act on the projective sphere, but it doesn't act on the circle. There is an abstraction which is in relation with the algebraic structure here and the topology here. And this beautiful theorem motivated a very important work by Gis and independently by Bourget-Monod concerning actions of what I said before, higher rank lattices in higher rank simple E groups, and they prove that this group cannot act, say, by C1 diffeomorphisms. So the question about action by homeomorphisms is still open. Okay, so this generalized this in that it considers more groups than before, but you have to impose this extra assumption. My contribution here really is on the following. It is well known by the work of Kashdan in the 60s that this group here, and actually all these lattices here, satisfied a quite remarkable cohomological property, which is called Kashdan's property T, which is very easy to state. So every action by isometries of such a group, by isometries of a Hilbert space, has a fixed point. Okay, this is a quite remarkable property of this group. Of course, this is satisfied by every finite group, but this is quite remarkable that SL3Z satisfies this property, and but actually in a certain sense, in a very precise sense, most groups turn to satisfy this property. So there is a notion of genericity in the world of groups, and most of the groups satisfy this Kashdan property. And the theorem, actually this was in my thesis, is that, say 10 years ago, more than that even, if you impose this single condition, this single cohomological property, Kashdan's property T, then you kill actions on the circle in the sense that every finite generated subgroup of the group of diffeomorphisms of the circle with this property is finite. Okay, and here the only problem is that you have to impose some extra regularity assumption. So the natural regularity here is this strange regularity here, which is 3/2, and it is unknown whether this it is really necessary or not. By the way, let me show a corollary in the spirit of what I say at the very beginning. If you take an action which is nice, then you will deduce something nice for the group. So at that time, this was the first proof of the fact that Thomson group T, the one that acts on the circle, doesn't have this cohomological property, Kashdan's property T. Okay? Why is that? Because T is a group of diffeomorphism of the circle because of the Gis and Sergius co-realization, so the theorem here applies. I will just give the idea of the proof of this theorem, because it is an elementary proof, which is in the spirit of the proof of Thurston. So let us start with a group of diffeomorphisms of the circle, and let us assume Cartan property T. So you have to build some isometric action on a Hilbert space to say something. So what is Hilbert space that I consider is L2 of the here. And an isometry of Hilbert space is just the composition of a unitary part and a translation part. So here I'm taking a unitary linear map, and this is just a vector in this L2 space. What is the unitary part? Well, quite natural. I will take just chains of coordinates that I will multiply by the square root of the Jacobian in order to make it unitary. Okay? And, well, you have to put a -1 here in order to make it equivariant, but forget about this. Now, the important point here is the C. The C has to be a vector that is well behaved with respect to this unitary representation. The right word here, it has to be a cocycle with respect to this unitary representation. And the C here is this nice formula. It's a function in two variables. It's just this. So what is the point here, the key point? So one of the key points. If you take this function here, this is not an L2 function. This function here is not an L2 function. But if you perform the difference, then you kill this singularity here and you get an L2 function. And for this, for having this property, you need this regularity. Okay? And this is a cocycle. This is obvious because this is a coboundary. In formal terms, this is a coboundary because you are taking the coboundary as the function, which is not in the Hilbert space. So this is a formal coboundary. So it's a cocycle, so you have a representation by isometries of a Hilbert space. So this is the mathematical object, and the rest of the proof is just an exercise. Once you have realized that you have something which is nice, the rest of the proof is, if this cocycle, if the associated affine action has a fixed point, then you get something geometric which is invariant, and then you start arguing. Let me just say why this cocycle here is so natural. Well, this comes from an exercise, which it's a very nice exercise for a course of calculus. A map is projective, say a map of the real line of the circle, if and only if it satisfies this identity here. Okay, this is a well-known exercise, and if you look carefully there, this expression is like the difference of this. Okay, so this is like taking the square root of each part. If you want an unfair solution for this exercise, this is related to the fact that there is a nice formula for the Schwarzenberg derivative of a diffeomorphism, which is given by this one. So if this expression here is 0, then you know that your map is projective. So now what we have here is 0, but in cohomological terms, and then you have to argue. But the general spirit of the proof is that you just need to compare. You are just comparing the action on the circle to an action by projective maps. Okay. So I think I still have 1 minute just to say two things. So I wanted to give some reference for this theory here, and well, I don't want to refer to articles. It should be almost impossible. I just want to say that there are many references, but I think that at least for me this was quite inspiring. So I learned from this theory by reading this monograph written by who was my PhD advisor, Etienne Gis. He wrote this very nice monograph for, I think, in '99 for a ELAME school in Peru. Then, well, we realized that there was something that wasn't covered in this monograph, namely this concerned actions by homeomorphisms, and the theory of actions by diffeomorphism is quite different. So I wrote this book here that I published in the same collection. There is another edition of this published in the Brazilian Mathematical Society in the collection of Ensayos Matemáticos, which is somehow a translation of this. And then this became more standard reference, so Etienne somehow improved his original version and wrote this very famous survey article in Enseignement Mathématique. And I translate and publish this monograph. This became a book in the series of Chicago lecture notes after a very kind invitation of Benson Farr. But of course, these are not the only reference. There are many other references here. For instance, I like very much this book of Danny Caligari that covers certain aspects that I didn't mention here, namely the relation with populations and three manifolds. So this is the standard reference for Kashtan property T. This is somehow the proceedings of this corresponds to the proceedings of a conference for the occasion of the anniversary of Robert Zimmer. So this contains more or less everything what was known up to 2008 about group actions on manifolds, about orderings. You have, I say, for the case of braids, you have this very nice book that covers both aspects, so the Hornois aspect and the Nielsen-Thorson theory. However, there are two forthcoming books that cover group theory, orderable group theory in a more general way. So this is from the Spirit of Dynamics, and the book of Dale and Adam Clay is going to cover the aspect related to topology. And just to close, let me just mention that this is a very hot subject. I think there are many things to do in this subject, so we decided to organize a conference next year in Chile in September about orderability and groups, which is somehow the second issue of a conference that was organized last year in Banff, and everybody is invited to this. So.